Hello, and welcome to Simply Space. My name is
Jeanette.
And I'm Shetta.
We are a group of students from Lamont High School co-working with Oregon National Lab cosmologist Steve Coleman. We're working with Oregon National researchers to gather and interpret data from the 4-meter diameter telescope in Chile for the Dark Energy Survey.
Our job is to simplify the wonders of the universe in fun and easily understandable videos, making the complexity of space much more approachable, hence our channel name, Simply Space.
We are here to tell you about gravitational lensing. Lensing may sound like it involves a glass lens, but in fact it has nothing to do with any kind of lens. It's instead a gravity phenomenon in space as observed many times throughout human history.
Now, before we get into the types of lensing distortions, let's find out what the science of lensing is like. A direct consequence of Einstein's theory of general relativity and an observational way to prove it is gravitational lensing. It requires a powerful gravitational source to work, such as a galaxy or cluster of galaxies. It works in a similar way to a lens of glass, where rays of light are bent toward a single source, increasing the brightness. In this case, instead of a glass, the bending of the rays is due to the curvature of space. Light rays coming from the source would otherwise miss Earth, but instead are bent towards us when there is a massive object in front of it. It's a concept that allows us to see galaxies near the edge of the universe, far more distant than other galaxies and clusters. Using computer algorithms, astronomers have found ways to make the distorted image from a gravitational lens and piece it into a usable image that can be studied. More often than not, the galaxy doing the lensing is not perfectly aligned with the source, or the Earth, giving a strange lensing image. But if they are aligned perfectly, we can end up with what we call an Einstein ring.
There are 3 types of gravitational lensing. First, there is strong lensing, which is when there is a strong visible distortion like the formation of Einstein rings, arcs, etc. There is weak lensing when the distortions of background sources are much smaller and can only be detected by analyzing large numbers of sources and to form coherent distortions of only a few percent. Lensing shows up statistically as a preferred stretching of the background objects perpendicular to the direction of the center of the lens. By measuring the shape and orientation of lots of distant galaxies, the orientation can be averaged to see the shear of lensing field in an area. This can be used to reconstruct the mass distribution of an area. Specifically, the background distribution of dark matter can be recreated. Finally, microlensing is when there is no distortion in shape, but it can be seen in the change of the amount of light received from the background object over time.
The most common effect is called the Einstein ring. These Einstein rings can look either like a complete or incomplete ring of matter around an object, usually a star. It can be seen in this picture. Until you reach the horizon, a black hole only curves space due to its gravitational force. It wouldn't cause a photon to do a U-turn. Instead, the photon would curve around the black hole, gravitational lensing, and proceed to travel in the same relative direction it was before lensing occurred. This process causes Einstein rings if the observer's location is in line with the light source and the black hole.
A very simple experiment you can do to experience lensing involves about a piece of paper, a pen, marker, a wine glass. Using the marker, draw down on the paper like so. Once you finish, place the wine glass on top of the dot in such a way that the dot is under the very center of the glass. Next, all you need to do is look through the top of the glass, and you should be able to see what is essentially an Einstein ring. Now take a look at this video so you can see in visual representation.
One easy demo for gravitational lensing just involves using a wine glass and a piece of paper with a dot on it. And the idea is if you're looking at an object, a distant object in space, if something comes between you and that object, it can distort what you're looking at. And this wine glass does a great job of distorting the image just like dark matter would, or maybe a black hole, or sometimes just other galaxies. And when we look out into space, we see light being arced just like this. And that's one of the tools we use to map out dark matter. And this is a simple little demonstration that you can have kids do in class. They can put different shapes, get different effects, and it doesn't really take any effort or any preparation.
This is similar to the astronomy picture because depending on what the white glass bottom passes through, it can distort the image just like a black hole, black matter, or other galaxies that can distort the image of the lens passing through space.
Additionally, another much more rare image you can see is the Einstein Cross. This appears as four dots that form a cross shape that also have an object in the middle of them. Once again, usually a star, these two objects may look completely different. However, they are made in almost the exact same way, with only one minor difference in the process. Now that we have identified the two possible outcomes, let's talk about what causes this to occur. First of all, you must understand that all galaxies constantly release light in all directions. So if the galaxy's here and we are there, the light will eventually reach us and we will be able to see the galaxies. The light will end like this and the light will be in a cone shape. This cone shape will eventually hit us. However, we will see it as a ring formed in the sky. The Einstein Cross is interesting because a mass having a spherical symmetry can only give rise to two images aligned with the lens in the galaxy. If the mass is concentrated with a small volume, only two images are produced by the gravitational lens. The light that is bent by this elliptical galaxy can only come out in four possible angles, and it is correctly aligned with us as it creates an Einstein Cross.
To end off, we saw there was a lensing test during the recent eclipse. Here is a photograph negative of the 1919 eclipse taken with a 4-inch lens in Brazil. This position of the stars are indicated by the horizontal lines.
Thanks for listening. We hope we broadened your understanding about gravitational lensing. Bye-bye.